Just a quick reminder, test 2 is exactly in 9 days, right? Test 2 is on sorting, chapter 2 only. So in this course, once you've written a test on a piece of work, it's over. We know. So it's a lot of shorter tests. Chapter 2 is almost on you, end of next week, so please just make sure that you keep up, yeah, because next week you won't necessarily have time to learn all this stuff. So keep up with it. Same story, same style. What you have to know, it is 50 minutes, you're writing 3004 next to Narga H. All the same style, the same template as test 1, multiple choice questions, right? And you have to pick everything that fits. I am remarking on test 1. Remember that if you want the extra marks that you are due, then you either have to give your test paper or a copy of it to Miss Daly, who will bring me the whole stack. And I will remark that. But I have a lot of marking currently, so I'll get there. Yeah.
For the project, it says on the spreadsheet that we need to use the classes provided in the textbook. Can we take those and kind of compile our own class out of all of the different ones? Do we have to use each one individually?
So,
can we make our own, do we have to use those classes as they stand, or can we make our own implementation of that sort of thing?
you can if you want to, but you don't need to. The project does not require you program those classes, but they're there. If you want to use them, that's fine. I'm going to test in the theory test whether you understand the algorithms. So whether you want to, I'm not testing that in the project again. I asked the demis to have a look on SunLearn. It's too much trouble to try and run a forum from the standard web page. So there will be a forum on SunLearn. I asked the demis to organize who checks it for questions. Specifically questions about the project. Please, please, please ask Francois Meyer, right? He's the head demi. Please ask him. He has the final say in the project. So he sets up the marking schedule. He has written both projects over the December holidays, so he knows what the issues are. If you ask me whether I can do this or must I do that, I will simply say, go ask Francois. Okay, because he's in charge of the projects. Unless you want to complain about Francois, then you may talk to me. Okay. Shouldn't, he's a very nice guy. Okay. So test 2 is sorted out. The tutorials. The tutorials are not per se compulsory in the sense that you need not go and sit in Narga H if you don't feel like it. However, if you're the type of person who wants to go to Narga H on a Friday afternoon, then the demis are there and they're there to help you. Especially if you're struggling with things, please make an effort to attend. Once you are there, you need not sit there for the whole afternoon, especially if you're on your way to Betty's Bay or Hermanus. What do you do on weekends? Or whatever. My days, it was Betty's Bay. I actually stopped taking applied maths in my second year because they had the TUT on a Friday afternoon. Terrible. Okay. And also maybe because I like computer science better. Right, so the TUTs are there for your use. What is compulsory? And I kick you out of the course and you fail if you do not by Friday afternoon at 5 have a GET submission. You must do a GET submission of the TUT at the latest Friday afternoon at 5 o'clock. To my knowledge, GET is open. You can do it anytime you want, as long as there is a submission of that TUT by Friday 5 o'clock.
How do we name it? Is it just TUT 1, TUT 2?
Yes. Because it is in the GET repository is yours, so it's uniquely identifiable that it's yours. The way I understand Andrew set it up, yes. Is that correct? If you want to, you really want to give your student number TUT 1. Okay. That's it. More questions? You can also do that submission from home, or you can do it from NARGH or whatever, but if I don't have a TUT submission by Friday afternoon, that is a compulsory assessment thing. You have to do it. Okay? Right? So if your GET is not working, make sure you talk to Andrew Colette, make sure you get it working by Friday. No excuses. Yes.
Will we also have submissions due on the Fridays and right as or demo appointments?
Yeah. The TUTs continue. So you'll see on the schedule, it says test 2, project 2 continue, project 1 continues. What is project 2? Can't remember which one. Yeah, so you have a submission even if there's a test. Tests are compulsory. Yes? Questions? You still happy? Good. Sorting. You have to look at that Java, and the Java has to make sense to you. You must know why it's I++ and not I-. Yes? You must really understand the code. Then, without having the code next to you, you must be able to work through an example applying that algorithm. Yes? So I won't ask you to reproduce the algorithm just as it is in the textbook up till every semicolon. But you have to know the code in the sense that you must be able to apply it without having it next to you on an example. And what's more, knowing the code, you have to know how efficient is this. Yeah? So you have to know the time complexity, the space complexity in tilde notation. You must know selection, sort, tilde notation, number of compares. Woo, mamma mia, 9 dae. Woo! 'n geween en 'n geknars van tande. N square upon 2 if I have it correctly. Or was that insertion? My. Okay, you have to know. Yes, selection is n square upon 2. Insertion is n square upon 4. You must know what you are measuring for each algorithm. Are we looking at compares? Are we looking at exchanges? Are we looking at array accesses? Okay? You must know the difference between them. You must know whether this sorting algorithm needs extra space or not. And you must know for the sorting algorithm, if I get duplicate values somewhere in my array that I'm sorting, when I have the final sorted answer, are those duplicate values still in the same order that they were in the original input? You have to know for the input whether input itself makes a difference to the time that the algorithm takes to execute. In other words, is there an average case, a worst case, and a best case? Are they the same or are they different? Which of the sorting algorithms we've covered are insensitive to the input data? Miss Daly, since I know your surname. No?
Yes.
Selection sort, insertion sort, which one of them is insensitive to the input data in the sense that whether it's randomized or already sorted or reversely sorted or all duplicates? Well, she had a 1 in 2 chance of getting it right, and she did. It's like when you listen on Cape Talk to the Brain of Cape Town sing, you can hear in the voice they're guessing or they're not guessing, but okay. But it was a good guess, yes. Is insertion sort, Miss Parable? See, there are few women, so I learned their names first. Is insertion sort sensitive to the input data? Yes, you think correctly. So you have to know, how does this efficiency change whether I have randomized input, if my input is already sorted, if my input is reversely sorted, and when all the values are the same, right? Selection sort is cool because it doesn't matter. Okay. Propositions you have to know. You have to know the result of the proposition itself for every single proposition. Not the proofs, where you need to know the proofs. I'll tell you the proofs. Okay, so let's look at selection sort first. Terrible, because we know it's n squared, right? And remember, in the beginning of the course, we said we are moving towards algorithms that can solve a given problem in time, logarithmic time, yes? So we cannot make, or mostly, not make it smaller than that, okay? So we don't want quadratic. Quadratic is bad. And to amuse yourself, call selection sort on Friday, and then, not with a phone, with a method call in Java. Apply to an example on 10 values, 100 values, 1,000 values, 1,000,000 values, and see how long n squared takes. Yeah, it's slow. It's really slow. Right, so what's the idea about selection sort intuitively? Neither am I. I think we're looking at selections. Selection sort. It's the first sorting algorithm. We are on page 249. What is the intuitive idea of selection sort? I take the first value and I look at the whole rest of the array and I say, what is the smallest value in this whole damn array? And I find it. I do the min operation and I put that one first. So I swap the min value and the one I had in front. That means that the smallest value in the whole array is sitting in position 0. Cool. It's already sorted. It is in its final position. Then I go to position number 1 and I compare all the values in the whole rest of the array and find the minimum value. That is the second smallest value in the whole array, and I put it in position 1. Okay. Then we see it's n squared. We don't like that. We want to make it a bit smaller. And where does our inefficiency come from? It comes from there where we're walking through the whole of the rest of the array, because we have to do it all the time. every single time. So insertion sort says, well, let's see if we can make the thing a bit faster. We don't want to look at the whole rest of the array. So as we progress, we don't look at the whole of the rest of the array. I just look, where am I? Compare it to the next element. And if those two are out of place, then I swap them. And I bubble back this value to its correct position in the small first part of the array. Right? That should be false. Yes.
Quick question. With the selection sort, for the first part, you look at a whole array, then you put the first one in. Then for the second part, you look at n minus 1 of the array, then n minus 2 of the array, then n minus 3. So isn't it n, it's not n squared, but n factorial n, maybe?
No, you're not multiplying, you're adding. Because the very first step, I look at n minus 1 elements. The next step, I look at n minus 2. So at how many elements have I now looked? N minus 1 plus n What am I doing in insertion sort? I'm just looking at two things next to each other. We're bubbling the one back. And then we didn't have time to finish show sort, and I told you to go and have a look at it. The tweak that we're going to do to insertion sort is we're going to say, oh, really? I'm creeping along, comparing two elements next to each other. It takes such a long bloody time. I'm going to increase the distance between the elements that are swapped. Yeah? Right? So I get that thing that they call the H value, yes, which you should now know what it is. Yeah? So I'm simply increasing that distance. So I don't compare elements next to each other necessarily. Okay, and that brings us then to that H value. Oops, Daisy. Okay, right. Actually, have a look. Look, it's like insertion sort. But instead of having AJ and AJ plus 1, I'm going to pick, or was it J and J minus 1? And the two things next to each other, I now have things a bit further apart that I'm comparing. And funnily enough, yes, look at that. I'm just comparing things further apart, not next to each other. And funnily enough, on a randomized input, it gives me a very good answer. If you implement show sort, you'll find that it's really, really, really efficient. It's comparable to these other advanced algorithms that we will do. Okay? So the simple trick of not giving baby steps versus making a jump gives show sort this increased capability. Okay? And that's really the only difference. Okay, so I'm finished with that. Those three algorithms are the basic sorting algorithms: selection, insertion, and show. And they are really, in principle, very easy to understand. I do a comparison, and which things do I compare, and where do I put my result? But we are still not where we are in terms of logarithmic performance. Okay. So now we're going to do merge sort and quick sort. I'm only going to do one version of merge sort called the top-down merge sort, right? And bottom up you can read yourself. As long as you understand top-down, I'm happy. In other words, bottom up is not in the test. Okay. I don't know if you've ever done this kind of sorting, but I do it every time I have student assessments that I have to mark. I get a stack of papers and I have to sort them in terms of student numbers. So what do? I look at all the less than student numbers that are less than 1/8 something, and I put them in one pile. And then I have all the student numbers that's 190, and then all the student numbers that's 191, and so on, and I make these separate piles. I sort each pile, and I put them in together. Yep, that's merge sort. You break up your problem into smaller parts. You sort the individual small piles. Then I have two sorted short piles, and I merge them together. Okay. So let's have a look at how merging works. Does that make sense to you? Okay. Let's see how merging works in terms of the data. The first point is that we can do the merging in place without using extra memory. But it's a bit tricky. So we are going to do it using an auxiliary array. So first, what we do in the beginning is we copy the whole array to an auxiliary. So I have my original set, and now I have the auxiliary values. And we have the idea that somehow the sorting will give me lots of different piles. Every pile has the smallest value and the highest value. Yes, so I have a low and a high in terms of the indices of the array. Here's my original array. 0, 1, 2, 3, 4 positions, right? Indices. If I break up my array like so, the piles incidentally of length 2, the lowest index in this pile is 0 and the highest index is 1. So lowest 0 and highest 1. If you look at that curve. In this pile, the lowest index is 2 and the highest is 3. Okay, so this is low, this is high. Right? So I do my copy, and what I now do, the moment you do this kind of technique where you break your problem up into smaller parts and solve it on a small thing, and hopefully the answer bubbles back to the whole thing, is called divide and conquer. It's like cleaning your room. Let's make the bed. Okay, that's done. Let's sort out the bookshelf. Well, you do it piece by piece by piece, and when you're finished, everything is finished. Divide and conquer. Right.
So divide and conquer is a technique that creates linear runtimes. I think so.
In this case, the answer will be no, so I can give you an example of it is not necessarily the case. It feels like it. This is a very good comment. It feels like I have n places to clean out in my room. So basically, I have to cover them all. But what we win by using divide and conquer in a Java program is by breaking up the problem into smaller parts. Remember that we are counting comparisons and exchanges. So if we break it up into small enough parts, we might, in many of those parts, not have to do any exchanges. And that is where you win, and therefore it is not the addition of all the individual efforts. Does that make sense? From a, you know, keep this hand waving and gut feeling. Yeah. Okay, good. Right, so let's just look at merge because the code is not necessarily obvious. Yeah. So if you give me two piles, one of them starts at low and the other at high, the other starts at low and the other starts at high, ends at, sorry. So the picture looks something like this. I have an A, I copy it to the aux array, yes, and now my aux is divided into two parts. Yes, it's 10 elements, so the first 5 and the second 5. And now I want to merge them. So the idea is very intuitively, just like you would want to do it by hand, is you look at those two parts and you look at the first part, the left-hand side and the right-hand side, and now you compare. So immediately I see that low in my left-hand side is here, it's an E, and low in my right-hand side, position 5, is an A. So I compare the E and the A. I see that the A is the smallest, and I copy that A into my original array. There, right? So this is my original array A. So I write the answer of the comparison in there. So I never did any exchanges. You see that? I did a comparison, but I did no exchange. Yeah. Exchanges are expensive. Remember when in the first year you had to swap the values of X and Y? 3 operations, so it's actually 6 array accesses to do a single exchange. I did no exchange. I did a comparison, but no exchanges. Cool. So I saved time. Yeah? And I continue. Yes, doing that. Now I look at the second one. I look at E and C. Yes? And I see that C is less than E, so I put my C into A, and so on and so forth. Okay? Now just double check that you follow the code. When would I stop? I have to ask myself, when would I stop doing comparisons? Well, suppose I compared, and my low went over the top of the area I'm looking at. So my low for the left-hand side goes bigger than 4. That means I don't have to look at the left-hand side anymore. I can just copy the rest of the right-hand side. If my high for the right-hand, my low, sorry. I is my left-hand side, J is my right-hand side. If my I is smaller than J, so J is running over my high, yes, then I'm just straight copy. I can stop comparing and just do the copy. Okay? Right, so I test whether I have to compare. Is my things running over each other? If I'm still kosher, I just do the comparison, and depending on whether aux J is less than aux I or not, I copy J over, otherwise I copy I over. You have to sit with that Java for a little bit and work through this example by hand, just to make sure that you agree with the Java. Okay? Okay? If you run through this once by hand, it makes sense because intuitively it's so easy. I have 2 parts. I look at the first element and the first element. if this one is less than that one, I write it in here. And now I'm still at this one, but I must continue, I must add to my J, and I go on doing that, copying. Okay. And that is merging. Right. So what happens with merge sort is since I want to divide a problem into smaller and smaller and smaller parts, what do I have to use? I have to use recursion. Okay? That's the one technique you have from the first year that does things, divide the array, divide each part there, divide each part here, recursion. Right? So to do sort, I'm going to call my sort algorithm, which is a recursive algorithm. And how do I divide my array? I find the midpoint between high and low. Yes. So low up to mid becomes this left-hand side, and mid plus 1 up to high becomes the right-hand side, and now it's divided into 2. Yes, so I call sort recursively on A, low up to mid, and A, mid plus 1 up to high. And the sort really are just allowing me, if you look at the trace over here on page 272, the sorts are just called, look at it carefully, until I have 2 elements next to each other. Yes, so I have 2 elements in, and I can merge. So I divide the problem into the smallest possible intervals, and I merge those. So sort, in a certain sense, in this code does nothing. It's just the recursive call until I get to merge. Yeah. So basically, you're writing a sorting algorithm without any exchanges. Because you're breaking up the problem into the smallest possible part, and then you finish, and then you merge it. And because I'm using the extra array, I have the storage space, and I'm just copying. I'm comparing, but not exchanging. And that's it. There we go, proposition F. Top-down merge sort. Uses between, yay, half n log n and n log n, compare. We logarithmic, yippee-yay-yay. Ready? Oh. This is no stenography video. Oh, that was a quote from a die-hard movie. It's just oh, yeah. Obviously, sorry. After this moment of great fun, it makes me feel that way, you know? I conquered this thing. I wanted to sort, and it didn't want to sort quickly. And now I got it to sort. Yes. Anyway, some people jump from bridges on a bungee rope, and I gave you an algorithm that can do this. It's an adrenaline rush. Right, okay, sorry. It was just pointed out to me that I said logarithmic. Of course, this one is actually linear arithmetic, right? Because it's n log n, which is linear arithmetic, okay? But that log made me so excited. Forgot about myself. Okay, so we know, do we know no exchanges at the cost of having an extra array. Now you have to ask yourself, if I'm working at the SKA, that large nearcut thingy with all the star data, and I have 1 billion terabytes that I want to sort, would this extra memory make a difference? And indeed, the answer is yes. I'd rather not create an extra array of that size. Okay, so at the cost of the extra memory, we get a lot linear arithmetic algorithm.
Die alle dividing functions is linear arithmetic.
Neither
Maar merge sort is altijd.
Yeah. And then right. So this is important to me. Remember in the first year book, we had the recurrence relations. Yes. Tn. Oh, heertjie, dit was nou weer in die eerste semester. Huh? Go back to chapter 1 in this book, section 1.4, how to solve a recurrence relation. We want to look at what is the maths. I can't sommer say that now it's linear arithmetic. I have to mathematically prove it, right? So when you devise your own algorithm for the insert name here algorithm, you have to prove to the world that this is really, really a great algorithm. So you have to give the maths to show that it genuinely is a great algorithm. Okay? So what we are going to do is we're going to put up an equation which describes the number of compares to sort an array of length n. Let's call it Cn. The number of compares needed to sort an array of length n is Cn. And then, just for a decent start, we say to sort 0 elements takes 0 time. To sort 1 element takes 0 time. It's just there. Yeah? It takes no time to do it. So, now we want to say, if I know that it takes this long to sort 3 elements, how long does it take to sort 4 elements? Okay. Now, in our case, we divide the thing into 2 parts. So I look at my n and I say, well, to sort n elements is the sum of the cost to sort the left half and to sort the right half. Okay? But we are not giving an equality, we are giving an inequality, less or equal. I know that it can take no more time to sort that thing, yes, with a plus n. Okay? So the number of compares, why do I have those extra n compares? The extra n compares comes from the merge algorithm. Okay, remember that I'm saying I'm looking at the number of compares. So it is the number of compares to sort the first half plus the number of compares to sort the right half plus the number of compares for the merge algorithm. So that third term is the merge algorithm. Okay? Right. Okay? Live with the n for the moment. What we are not saying that it will take n compares to merge. We are saying that that n is an upper bound. It cannot take more than n compares to sort. And then we throw it around. And we say, well, what is the least number of compares that we do? Well, the least number of compares is the sum to sort the lower half and the sum to sort the other half, and it cannot take less than half n to do the merge. Go look at the merge code again. Write down a small array of size 5 and convince yourself. Okay? Write it out. Count it and see what happens. Right. Now we have 2 inequalities, an upper bound and a lower bound. So we know the value is somewhere in between. We have 2 inequalities and we want to solve this. I think mostly up to now, most of the maths you've done was exact solutions, if I have an equal sign. But you sometimes get these dilemmas. I know that the true answer for my specific n lies somewhere between this value and that value. So we approximate. Yes, that is an approximate answer, but I cannot say more about it. So to solve it in this case, and this is a very nice trick, we say, well, I know if that n that I have is a power of 2, then I can change those two inequalities to an equality. Okay, so it's a maths trick. It's maths. As computer scientists, we sometimes want to understand the meaning behind all the math. Math is mechanical. It's a trick I do. Right? It's intricate in detail, but it's not necessarily that deep. So that is my trick. I'm looking at a specific value of n, in this case 2 to the n, and if n is a power of 2, then I can write it down as an equality. Right? So we set n to 2 to the small n. So now big N is a power of 2. So I'm doing my proof only for n a power of 2. Well, then the floor, if n is a power of 2, both the floor and the ceiling of n upon 2 is obviously 2 to the n minus 1. Hallo, juffrou De Bruin, maak dit sin. Hoekom sê ek nou daai? Want wat is, ek het 'n n wat 2 to die mag n is. Ek het 'n n wat 2 to the mag n is. And now I divide it by 2, therefore my answer is 2 to the n minus 1. And the floor, you remember the difference between floor and ceiling? Yes, that's when you have a value that's not divisible by 2. You take the lower or you take the upper answer. 7. Verveel ek julle of julle net klein. The floor of 7 divided by 2 is 3. The ceiling of 7 divided by 2 is 4. I round up or I round down if it's not an even division. Okay? Right. And now I just solve this thing. Yes, I just put 2 to the n minus 1 in that upper one. Yes. Oh, the other one, the upper down. I take this one and I substitute that big N with the 2 to the small n. Okay. I fill it in. There I go. 2 to the small n, it is the floor plus the ceiling, so it's 2 times 2 to the n, c 2 to the n minus 1, plus big N, which is 2 to the n. So I get that from the first inequality. Okay? And then I just do a bit of maths. Yes, which I can go through painfully, but I'll do it quickly. I divide by 2 to the n, you can see there. I do a division of that thing divided by 2 to the n, but if I divide on the left-hand side, I must also divide every term on the right-hand side, so I divide by 2 to the n, yes, and it was 2 times that, therefore I get the 2 to the n minus 1 there, plus 1, and I keep on doing that. And doing that substitution in the first term, if I have a formula for c2 to the n divided by 2 to the n, then I can clearly have a formula there as well. Yes, so I substitute in that first term all the time, and I get a plus 1, plus 1, plus 1 all the time, and I end up over here. We know that 2 to the 0 is 1. And C2 to the 0 is C1, which is being defined as 0. So this is 0. So C2 to the n divided by 2 to the n is n. And off you goes. We get C of big N is just C of 2 to the small n, which is n times 2 to the n from that one. Yes, can you see that? There I had n, C 2 to the n divided by 2 to the n is n. So multiply by 2 to the n here, so I have to multiply there, and that gives me. Cool. And that you have to know for the test. So I will write something like, prove that, blah, blah, blah. Prove that top-down merge sort uses between that and that to sort an array of length n, and then you have to write down this whole proof form. Okay, you have to know this by heart. There's an explanation on why it makes intuitive sense, because you're building a tree. There's another one, the array accesses. We manage not to do any exchanges at the cost of making an extra array, copying to it. But if you copy between two arrays, you have to make array accesses, right? So you have to know that proposition. And then the very bottom-up merge sort for your own gratification. And then this proposition and its proof is for homework, and it may be in the test. Yes? You have to learn how to read the math. If you get stuck, I'll answer questions tomorrow morning about this one. Okay? Makes sense. You have to learn how to read the proofs, because in 2 years' time, when you're doing honors, you have to produce the proofs. Okay? Out of thin air. Read this. It makes sense. It's all in terms of trees, which is the thing we like as computer scientists. So actually, this is a fairly easy proof, although a long one. Right? And tomorrow morning, we start with quicksort. Great. Thank you very much.